Welcome and thanks for tuning in. In this demo, we'll be showcasing some of the API security capabilities of the F5 distributed cloud platform. We'll walk through a few attack scenarios and follow up with different ways to defend against them. Throughout the demo, we'll be viewing the data through the analytic lens provided by the platform. In the table view of the API inventory, we can see some of the additional data discovered for each endpoint. We can see discovered sensitive data types, the threat level of the API based on volume of attack traffic, the authentication status, API category, and calculated risk score. Now, if we sort by the risk score, we can see the contact mechanic endpoint has a score of 90. So we'll dig deeper into that and see why that is. If we click on the endpoint, we can see additional details related to its health, behavior, authentication, both learned and inventoried specification, and security posture. We can see that in addition to some issues with the JSON web token, the API is passing a URL inside the request body. This means we're vulnerable to an SSRF attack. We can see the description of the vulnerability, a link out to the evidence, and remediation recommendations. There are a few options for remediation. We can fix our application, check the schema to see what it's looking for and turn on validation. We can configure a rule and use regex to enforce the allowed values for the URL, or even enable WAF and SSRF signatures. Next, if we click the evidence link, it takes us to the request monitoring tab filtered to the request ID. Here we have the base64 encoded body, and if we paste that into a terminal and decode it, we can see that not only are we vulnerable, but an SSRF is occurring. Luckily, it's only to Google search. Now that we have visibility into the SSRF vulnerability, we can go ahead and start remediating it. As we saw, this could be done in a couple of different ways. To start, we'll modify our OAS and turn on schema validation. Here we have our spec, and we can see that it is simply looking for a string. Clearly, that's not enough, so we'll modify that to check for a specific pattern. We can also see that there's no limitations put on the number of repeated attempts. We'll fix that while we're here by setting a maximum of 5. Now that we've updated the specification, we need to upload it to our API definition and move to a positive security schema validation model. We just upload it directly to the initial specification and give it the same name. Since we're only versioning and not overriding the file, all of our previous specifications will remain available to us. Now we'll edit our inventory validation enforcement type and set it to block. And as easy as that, we've remediated our SSRF vulnerability. We can now review the security analytics and see that further SSRF attacks to the contact mechanic endpoint are being blocked. On further review of the logs, we can see that some calls to the coupon validation endpoint are being blocked as well. We should check to make sure that we didn't break anything when we changed the validation model. The alert appears to be valid, and something being passed in the coupon field is a violation. We also have a WAF alert for the apply coupon endpoint that looks related. Checking our logs, we can see our coupon processes are under attack by a SQL injection. Since validation is already protecting our other verify coupon endpoint, we can set the WAF to blocking mode to ensure we fully mitigate the attack. It's easily done by editing the app firewall and changing the enforcement mode to blocking. Now if we head back to the security analytics and hit refresh, we can see that we are now blocking the coupon fraud attack. If desired, we could also add the attacker to the blocked client list directly from here. In this mass assignment scenario, we've just been told by our development team that there's a flaw in the business logic of the create order API, and if someone passes a negative number in the quantity field, it increases the attacker's wallet contents by the amount it should have deducted from it. If we check the specification file, we can see that it only requires an integer. We need to put a quick fix in place to stop the attacks, so we're going to use a service policy with some regular expressions to make sure that the value is a whole number. To do this, we edit the load balancer, navigate to the common security controls, and set it to apply specific service policies, then create a new policy and add our rule. We leave it at deny, set our method to match what the API expects, and set our path to the exact value we're applying the rule to. In this case, workshop, API, shop, orders. Next, we toggle on the advanced fields to show the request body matcher and add our regex. Finally, we apply our new rule, add the fall-through rule, and save our work. Now we have a quick fix in place while the dev team works on fixing the application. If we look at the analytics, we can see that the service policy is blocking the attack attempts, and if we know this is a bad actor, we can go ahead and add them to the blocked clients directly from our alert. Another way we could mitigate this vulnerability is by modifying the specification to ensure that negative numbers don't pass validation. Now, similar to what we've shown before, we just edit the API definition and upload the latest version of the specification. Once complete, if we check the logs, we can see that validation is catching the attack as well. Now we'll head back to our API table and check for more APIs with a high risk score. Here we can see that our getOrder API also has a risk score of 90, so we'll investigate that. Like before, we select the API and bring up the Security Posture tab. And here we can see that the service is detecting that even though the spec defines auth for the endpoint, requests are being passed without the auth header and receiving a 200. We could alter the API spec to resolve the issue, but this time we'll use another feature of the platform, an API protection rule. We can create these rules, as well as any rate-limiting rules, directly from the Posture tab. When we click Configure, we are brought directly to the rule creation flow with the endpoint and method already populated for us. We just give it a name, leave it at deny, toggle on advanced fields, and under HTTP headers, choose Add Item. Here we provide the header name and the match options. In this case, authorization and not present. Now we just save our work, and any requests with the auth header not present to this API will be blocked. Now back in the table view, we can click the three dots at the end of the API entry and go directly to the analytics for the endpoint. As you can see, the attacks are now being blocked. We can also see that if the enforcement mode had been set to block for this endpoint, schema validation would have blocked it as well. These are just a few of the runtime monitoring and protection capabilities of the platform. But really, it's just half the story. The other half involves utilizing secure coding practices, testing the OpenAPI specification prior to production deployment, conducting API threat surface mapping, and penetration testing your APIs after deployment. This will give you a well-rounded, defense-in-depth API security strategy.